In the last lesson, we talked about the different ways that you can quantify the tremendous scale of astrophysics. Because really, meters isn't going to be a useful measuring tool when we're talking about the distances from here to the nearest star, or even from here to the moon. So instead, we're going to be using things like light years, parsecs, and astronomical units. Today, we're going to be focusing on the calculations that are going to be really important for us moving forward when we're talking about trying to understand how far things are away from us, but also more details about those things. Specifically, we're going to be looking at stars today and the different quantities that we associate with stars, as well as the mathematical relationships that help us uncover those hidden quantities. So as a reminder, these are the three different measuring distances that we talked about last lesson. So the light year, the astronomical unit, and the parsec. Really today, we're going to focus primarily on light years and parsecs. Typically, a star is going to be given to you in units of parsecs because that's how we actually measure how far a star is away from us. But then, of course, you'll need to convert from light years into meters if that's the proper unit for the calculation. In your data booklet, you are given all of these things, so you can expect that anytime I would ask you to calculate it, or anytime you're asked, you will always have access to these measurements for light year, parsec, and astronomical units, and you'll just have to do some conversions using dimensional analysis when required. Now today, these are the five main properties that we're going to be coming back to over and over again. Distance, brightness, luminosity, temperature, and radius. And I expect from given information about a star, you should be able to calculate or discover all five of these things. Now the reality is, measurements that we can take here on Earth really only get us to these first two, distance and brightness. But there are some really important relationships that we're going to remind ourselves of uh, that will help us use these two measurements alone to find everything else. And this, I think, is super cool and a really, really powerful uh, tool in physics to be able to use these quantities to discover more about something than we're able to measure directly. Now, for just ease of remembering these things, I'm going to put them down on the bottom here, and we're going to come back to these throughout the lesson, um, kind of practicing one piece at a time and then putting it all together at the end. So we talked a little bit about parsecs and how we use angles to find parsecs in the last lesson, but we didn't really talk about like how that's actually used as a measurement. Now I want you to do a little experiment here. Wherever you may be, you can do this right now. In this experiment, I would like you to take your thumb, and at arm's length, close one eye, and then close the other. And you should be able to see your thumb jump back and forth in relation to the more distant objects that you're able to see. So, for example, like if you had a house across the street, if you're looking with your right eye, you see something different than if you're looking with your left eye. And the reason for that is your right eye is looking at your thumb in relation to everything else at a slightly different angle than your left eye is. So if you are measuring something that is um, noticeably closer or significantly closer than the things around it in that same field, you'll see it changing throughout time. Now, if you're going to do this with a star, look at a star with your right eye versus your left eye, it'll look exactly the same because the spacing between your eyes is nothing compared to uh, the distance some stars are relative to others. So if we want to see any measurable distance for measurements that we can take here on Earth, we need to get as far away as possible. So get two very dramatically different viewpoints. Now, we are pretty fixed here on the planet. Like you can take a measurement here in your backyard and then go across the globe to see like in China and then measure it again, and you'll get a difference, the difference of the diameter of the Earth, but even that isn't really enough. Instead, we're going to use the fact that Earth orbits the sun. So here, let's imagine that we are here in May. we can take one measurement. Then 6 months later, when we're on the opposite side of the sun, we can take another measurement. So imagine that these two positions are like your two eyes. And when we do that, we see that there is going to be a more noticeable difference in the angle that we are looking at this star. Now, this drawing is dramatically out of scale. Um, so in reality, they're basically parallel lines, just ever so slightly moving towards the center so that they intersect. Now, we are going to define some of this stuff here. This distance, if we say that that is a distance in parsecs, is related to this angle in arc seconds. We're going to use d to describe the distance. That is equal to basically the reciprocal of the the parallax angle in arc seconds. We'll define that with a p. This is a really simple relationship that if you have a value in arc seconds, just take 1 over that value and you'll get a distance in parsecs. What this actually looks like, because that diagram doesn't do a great job of showing you like what does your measurement actually seem to be. Uh, the reality of this is imagine that you're looking at the night sky and it looks like this picture here. That pink star is the one that you're really trying to observe. Now, 6 months later, from January to July, you take the same picture, but you notice that just that one star is changing. The reason for that isn't because the star itself is moving, it's because that star is significantly closer to you than the other stars in the night sky. So it's kind of like these stars here are like that house across the street, and then this star is your thumb stretched out at arm's length. It is jumping back and forth from this January to July because it is significantly closer to you. So that means that this only works if you are measuring a fairly close star relative to a field of very distant stars. So, give you an example of what this looks like. The star Betelgeuse, which has been in the news quite a bit recently because it's been changing its brightness um, more than we have seen it do in the past. It has a parallax angle of about 7.7 times 10 to the negative 3 arc seconds. So now we're looking at milli arc seconds, which is a very, very tiny parallax angle. We can calculate the distance if we take it through these steps of dimensional analysis. Here, I give you the relationship from parsecs to light years. Then you know the relationship from light years to meters. And you know that this relationship, the distance in parsecs, is 1 over arc seconds. So you should be able to take the arc seconds, turn it into parsecs, parsecs into light years, and then light years into meters. If we plug that in, to find the distance in parsecs first, we have 129.9, about 130 parsecs. Now that, of course, I want to know in meters. To get that into meters, we're going to multiply by conversion factor to get to light years, and then a conversion factor from light years to meters. And we end up with a grand total of about 4 times 10 to the 18th meters. So this, from an angle, we can calculate a distance in meters. That is our first of these 5 properties. So these two values of luminosity and brightness are going to be our next two in this set of 5 that we care about for stars. Now, luminosity and brightness are different from each other. We're going to describe luminosity with a capital L when we refer to it in equations, and brightness will take on a lowercase b. Now, luminosity is a measure of how much power a star is emitting. So a bigger star emits more power than a smaller, colder star. We're going to measure that in units of watts, which is kind of interesting. That we'll measure how much power a star emits using the same unit that we measure how much power a light bulb uses, or how much power you create when you run up the stairs. Um, Luminosity feels like what you are experiencing when you look up at the stars or look at a light bulb, but luminosity is not actually what you are sensing. Luminosity is relative to the object itself. Now, the thing that you are sensing is actually brightness. Brightness is a measurement of intensity. It's how bright the star is to your eye. Now, brightness or intensity is going to be measured in watts per square meter. This is the same unit that we used in our last unit, the energy production unit, when we talked about intensity. Watts per square meter is our brightness. Now, this depends a lot on the observer's distance from that object. Now, if you are really close to a light bulb, it doesn't matter how many watts it is, it's going to be bright. If you're really far away from even a very, very bright source, a very, very luminous source, it will look fairly dim. So that distance will change your intensity because the light is emitted out in that sphere. And the farther and farther you get out, just like the walls of a balloon stretching, the dimmer and dimmer it gets because it just gets more spread. And we can calculate brightness in relation to the luminosity in the same way that we were able to calculate intensity in relation to the power. Now, brightness is going to be just the luminosity divided by the surface area of the sphere, where the radius of the sphere is the distance you are from the object. Basically, you are sitting on a sphere surrounding that object. So say you are here on the planet Earth at a certain distance from a star. That distance is the one that you're going to use to calculate the brightness. So if, let's say, distance is x, we say brightness is b. But if you double the distance, since this distance is squared in the relationship, you're going to take that brightness and you're going to divide it by 4, basically 2 squared. If you triple the distance, it's b divided by 9. What would happen then? Just think to yourself, if you quadruple that distance, how much would you have to divide the brightness by? Of course, 4 is 2 squared, 9 is 3 squared, 4 squared is 16. So since brightness and luminosity are different, it is important to talk about, like, in practice, what that means for us. It's possible for stars to actually have the same brightness, that they look exactly the same in the night sky, but they are different distances and different luminosities. So what that could look like is, say you have a fairly dim light bulb that is a certain distance from you. You can make that light bulb look exactly the same as a brighter light bulb as long as that brighter light bulb is farther away from you. So if you combine those quantities in just the right amount, so that it's just far enough away that its brightness cancels out with that distance, then they can have the exact same brightness but different luminosities. If I want to come back to this Betelgeuse example, the star Betelgeuse has an apparent brightness of 2 times 10 to the negative 7th watts per square meter. This is a measurement that can be taken using instrumentation here on Earth. Basically, how bright in watts per square meter is the light from that particular star. Using the distance that we calculated in the last example, we can actually calculate what the luminosity of Betelgeuse is going to be. So we take this equation and plug in our brightness and our distance, solving for the luminosity, making sure that we are using that 4 pi r squared. We can calculate that the luminosity is about 4 times 10 to the 31st watts. That is a huge amount of power being emitted by the star Betelgeuse. So now we have calculated the distance, we were given the brightness, and we've calculated the luminosity. So we just have 2 quantities left for this conversation of calculation.